What's up, guys? It's Charles. How are you guys doing? We guys having a great day. Um, Except for today's video, this is the first video gonna be on math, particularly AAHL. Okay. But although this is for AAHL, a lot of content we'll be going through includes like some units from ASL and AI. So, and if you don't want to learn the HL content, it just skips through, and I'll try to link timestamps down below for you guys. So yeah, let's get right into it. So in this video section, we'll be covering scientific notation. So these are SO content, as the sequences, some applications, exponents and logs. Um, we'll have some proofs. We'll have the binomial theorem, the counting principle, partial fractions, and a lot of things about complex numbers. And this is the general order that the curriculum gives, but it won't be exactly the order that I'll be talking about today. I'm gonna start off with complex numbers because I think it's the hardest part of this unit, and I try to go along with the curriculum, but sometimes I like combine units to make it faster and easier because you know I'm making this in a bit of a hurry. But yeah, all right. So let's start off with some complex numbers. Okay. So first of all, we need to learn what the IB says about complex numbers, and this isn't like particularly universal, but you need to be very familiar. So the conjugate, the modulus, and the argument. So this is how the things I'm studying is how that they're shown in the test. So when you see this, you gotta think about the conjugate and modulus and the argument. So basically, what a complex number is you have a real number and you have imaginary part, and the imaginary part is I. And I'm sure you guys learned it already because I squared is equal to -1. That's basically the entire thing of it. And what complex numbers I like to think about it is I want to think that we're plotting on a chart. So this is the real number and this is the I. So if you have 5 real and 0 I, your point is here. And if you have 5 0 and 5 plus like 5 I, your point is here. And basically that's what this part is going to be about. So when we're talking the forms, the conjugate is going to be A minus BI. So that's what the complex number is going to be about. And so, sorry, the conjugate is given that it's expressed as a plus bi. Okay, that's how the Cartesian form of complex numbers are displayed. Given that this, we know that a is a real part of z and b is the imaginary part of z. So z is a complex number here. The modulus would be the distance from the point plotted on the graph to the origin. So using the Pythagorean theorem, we know that it's a squared plus a squared plus b squared, and we take the square of that to get the distance, the diagonal distance. And the reason why I want to get this is I will see later. But anyways, that's how the modulus is used, and you gotta keep it in your mind at every single situation. Now the argument is gonna be the angle, so it's gonna be an angle you're gonna find, and the formula for that is the inverse tangent of b over a. So you're basically using trigonometric properties again, and do remember that you want to adjust your quadrants. So depending on the quadrant you are, here are the rules that you want to adjust them for. So yeah, and there are gonna be 3 forms. So this might look like a lot of content, but I'm combining 3 subunits into this one section to make it easier. So we have the Cartesian form written as a plus bi, the polar form, which is r and then cis. So we can write. So basically, this is also interchangeable with cis of theta. So we have r cis theta and the Euler form, which is re to the I theta. And these forms are interchangeable, okay? And basically how you can do this is by finding the modulus and argument and exchanging it with each other, depending on the polar and Euler form. So the argument is going to be the theta in this situation. It's going to be the argument that you're trying to find. And the r here is going to be the conjugate. Conjugate. So you want to be able to be very familiar with exchanging between these different, you want to be exchanging between all of these. And remember that not only do you need to know how to go from Cartesian form to Euler form, you also want to find how to go back from Euler form to polar form or polar form to Cartesian form. So be very familiar with the rules of this changing. Yeah. And here are the operations that we use. So for Cartesian form, we want to combine real and imaginary for addition. And for multiplication and division, just keep in mind that, again, I squared is equal to -1 and make your necessary adjustments according to what you want to calculate. And for the polar form, you can't really add them easily, so you want to convert it back to Cartesian form. And how you multiply and divide is really easy. So here are the formulas for it, and I'm not gonna explain how it works, but for the sake of the test, you really do need to know this. So you're basically multiplying the moduluses with each other and adding the arguments with each other. So yeah. And on the next page, we'll find how to operate with Euler form. So Euler form is basically very similar. So R1, R2 times together for you can't do it for addition and subtraction again, so you want to convert it back to Cartesian form. And for multiplication and division, you want to be able to be familiar with how these different modulus and argument work. So yeah. And the one most important theorem that you'll get to know is De Moivre's theorem. So basically, it's saying like Zn. Okay, so we know that Z is a complex number, and R is its modulus, and zeta is its argument. So the nth power of this complex number is gonna be equal to Rn cosine of n zeta plus I sine of n zeta. That's right. And the reason why this works, again, if you really think about it, the powers is multiplying a lot at a time. So if you want to look back at over here, you'll see that it's basically multiplying by a lot of times. So that's why we're multiplying the zeta by n times. And this is really useful when you're trying to find roots. So when you're trying to find roots of a complex number, you're saying like, I want this root, which is like a fraction of the exponent. So this is a rule for it. And how I like to think about this is, again, I want to plot on an Argand diagram and say, okay, so for this complex number, I want to find the roots. And it can tell you how much roots you need to find, and you need to be sure to be able to know how to use this formula to be able. So um, I can't really think of an example on top of my head, but you want to keep in mind that k is the which root you want to find, and k will start from 0. Okay, so you don't want to get the addition wrong. You can. It's also useful for deriving trig identities, so you'd be able to derive how these cosine and I sine works, and as you divide this, you'll be able to like combine into a lot of different applications and questions, and it's even used with like you'll get to use the binomial theorem and things like that in the future. So it's also really important to know. Yeah, deriving the trig identities through it. And here are some extra notes I have for it. So roots of unity is basically the roots of 1, and you want to remember that these are evenly spaced alongside the Argand diagram. So these angles should all be the same, and it should all converge at the origin, because that's how complex numbers work. And again, cis of zeta, like it's basically cosine zeta plus I sine zeta. It's the same nomination, it's just in different form. And the Argand diagram. So I've got a lot of questions, and I think it'll definitely come up. It asks you to find the roots, and it'll ask you to find the area of these roots plotted on Argand diagram. So what you want to know here is you're gonna be able to use the SAS area, so the angles between the roots and the distance of the roots respectively, and you're gonna be able to find the areas of these things. And then you gotta remember to times it by however many roots you have. And another really useful thing to know is using the sum of roots. So the sum of roots here, and it'll help you figure out like maybe on what root it will be. And lastly, if you want to excel in the complex number unit, you need to know a lot of trig properties. So it's on your formula booklet, but when you want to see these questions, I want you to say, oh, I know this formula. Let me go find a formula booklet. So that'll be very helpful and very easy for you. Okay, starting with I think there's much easier than complex numbers. Sorry, I'm not talking really fast over this, because in a class you'll have to like so much practice and so much content, but I think this is just a really last minute review for me, and maybe for you guys as well. But I want you to like look over what I'm saying and say, oh, do I really know how to do this? And maybe you can stop and like try and find some practice problems, because that's going to be helpful, because you can't get good at math without being familiar with the subject. Like you can understand it, but you gotta be able to do it as well. And especially for complex numbers, it's really easy to make a lot of mistakes, and there's so many types of problems. So, yeah. Scientific notations, nothing really important here. Um, you guys know what it is. It's used for really big or really small numbers, such as like Avogadro's constant or other things like that. I just want to remind you guys that in IB tests, if you want to round to a number, try to round to three significant figures. If you guys don't know how to count that, it's your problem. And that's what the IB wants. And I've gotten mark taken off because I didn't do three sig figs before, so do keep in mind. And for operations of scientific notations, it's basically really similar to exponents, so I'll talk about that later. Now, arithmetic sequences. So, arithmetic sequences is like a series of numbers. I mean, a sequence. So, sequences versus series. IB won't really test you on the wording, but it's just good to know. So basically, it's a bunch of numbers, and their common difference is the same. So from A1 to A2, it's plus D. From A2 to A3, it's plus D. And D is normally the notation for a common difference. And here's the two formulas you need to know: finding the nth term and a sum of terms. So like within like Sn, like what's the sum of from A1 to An? And these are formulas you will need to use. I think it's your formula booklet, but I think it's helpful to know them by heart. And here's something to watch out for. So when you have A1, A2, and A3, and you guys remember that A1 plus A3 will be equal to 2 times of A2. Why is that? Because A1 is D less than A2 and A3 is D more than A2, and that will come back to help you in the future for a lot of different questions. And another thing is if you want to find the sum from like the nth term to the k term, you want to find the sum of all terms from k and minus them from the sum of all terms from n. So that's basically gonna get you the sum of all the values from n to k, because you're taking everything from k and minusing from everything like before n. So yeah, be sure to include n as well. Just saying. Geometric sequences is basically a really similar idea, but except for the common difference as a common ratio. So how does this work? So maybe you have like 1 and then 2 and then 4. So all of these have a common ratio of 2. And when you're finding the nth term, you want to be able to use an is equal to a1 times r of n minus 1. So basically like how many times you're increasing by the common ratio. And the sum of terms, there's two different forms for it. It's basically the same thing. And the one thing about special geometric sequences is that if the absolute value of r is less than 1, then the sequence will slowly converge, right? Because if, for example, if r is 1/2 and you start at 2, you get 2, 1/2, 1/4, and so. So what happens here is that you can actually find the sum of the infinity sequence, because all the values keep getting smaller and there's eventually a limit. So the formula for this is a1 divided by 1 minus r, and this only works when the absolute value of r is less than 1. Okay, so the geometric sequence is converging. And some things to watch out here, I think, are that geometric sequences, they really are tricky, and there's a lot of ways that they can be worded that you don't recognize as geometric sequence. And we'll get to see that in the financial application part. So 1.4, I think, is a really tedious subunit. So it's basic geometric sequences, but with money. And there's only one formula you need to know, but if you do really need to know that well. And I want to tell you guys, learn to use the financial application on the GDC. Um, if you're allowed a calculator, it just really saves you a lot of time. So learn like all the values and what you need to put into it. But for the formula, you want to learn like how interest works, right? So when you put some money into a bank, the bank will charge you interest like maybe every year like 5%. And you want to be able to use this to think about like how much money do I get after like how many years, for example. And the way that question is worded, that out of all these values, it's gonna give you all the values except for one of them, and you got this deuce that one out. And there's many different variations to this question, how financial application is tested. So, for example, the interest might not go up. For example, if you're buying a used car, like every year the value goes down. So you gotta know like how do I calculate like what if the value goes down by how many percent? Inflation. What if like the over inflation goes up, so the actual true value of this item isn't going out as much? So what you want to do for inflation is you want to calculate how much is the future value and calculate how much is the inflation divided by the inflation. And lastly, payments. Like I really rarely see these type of questions, but there's this one variable on your GDC that's about payments, and payments are like maybe I pay $50 back every year to like decrease how much the interest will increase. And I think that's more applicable on your GDC, but just be aware that this type of question might occur, even though I've never seen it. So, okay, let me drink some water. Sorry. 1.5 and 1.7. Let's talk it all about exponents and logarithm. So, this is a very formula based unit, I think. So, the rules of exponent: when you're multiplying exponents with the same base, you want to add the power. When you're dividing them, you want to minus it. If it's a negative power, it's the positive power under 1. Okay, so it's 1 over the positive power with this one. By the way, all of these are super important. I swear to you guys that you will see these, okay? And if it's a power of a power, you want to multiply these powers, okay? And if it's a power over another power, it's basically saying like the root of this. And this might look a bit confusing, but for example, like maybe x to the 1/2 is just equal to the square root of x. You don't even write this if it's 2, but it might be like this cubic root or something else. So logarithm is very closely tied to exponents, and I think there's, apart from formulas, there's one idea that I want you guys to be very familiar with. I mean, and it'll be really helpful. So I want you guys to like naturally think about the relationship logarithms and exponents. So when a of x is equal to b, then x is equal to log a of b. So when the base is a, you want to see how many sorry. So there's a and b, right? And you want to put a at the base, and you want to think how many power of a do I need to reach b, and that's how logarithms work. So this might sound really confusing at first, but it's like a relationship that you need to get very clear of, because you need to convert between these a lot of times. And this is the formula for adding them, formula for minusing them. And these go both ways, by the way. So if you see minus, it's basically dividing within the same log. And for these three formulas, I lied. For these two formulas, you want to ensure that the logs have the same base, okay? I didn't write it here, but logs can have different bases, and you want to make sure that you're working with the same base, or else it won't like fit properly and the formulas won't work. And for the last one, log of x to m is going to be equal to m log of x, because I'm not gonna prove here. Maybe I'll have another video about it, but it's kind of late now and I'll get this done with. Damn, my computer's almost out of battery. And lastly, though, I think one of the harder parts of this unit is the change of base. So changing a base means that, for example, if the base was originally something and you didn't like it, you can use this formula to get it easier. And I think an example of this might be like, how much is like, what is x if 32x is equal to 16? Like, what does this even mean? And a common usage of logs is you want to put it on both sides. So maybe log of this equals log of that. And using the change of base, we can like have log of a equal to 2, because 16 and 32 is both like both like power of 2. And so we can figure out this slowly using the change of base. And maybe there's gonna be one or two questions about it, but make sure that you do get these questions right, because it's relatively easy compared to like really ones focused on calculating or like really wordy application ones. So 1.5 and 1.7, this is basically all there is to exponents and logs. But all these formulas are super important, and they're used in more questions than this unit. So this is like crucial knowledge. What's next? Proofs. There's 4 types of proofs. The easiest is simple proofs, so you only change one side and match the other. And you're using algebra here, so you want to be very familiar with your techniques, your calculations, and make sure that you can manipulate both sides. So you just want to change one side so it looks like the other side. Proof by contradiction. So we got this one down. Proof by contradiction. So for example, you want to assume that, for example, if square root of 2 is irrational, you want to assume that, oh, square root of 2 is rational. And what is the definition of rational? It means that square root of 2 can be represented as like a over b. And then you go on to prove why this will contradict itself. And if this contradicts itself, it means that in turn, the assumption that it is false, which means that this will be true. Proof by counterexample. I don't think it's the most useful proof, but if it comes up, you're lucky because it might be like really easy. You just want to find one value where the proof doesn't hold true for all that it claims to hold true. So if one of the values doesn't really work for this proof, it means that this isn't a proof and the assumption is false. And the last one that I think most people and me, sorry, need some practice on is proof by induction. So there's 4 steps to it, but I wrote 5 steps just to make it more straightforward. So I want to propose your claim, and the question will give you the claim, and you want to show that for the lowest value that it claims, for most example, it's gonna be 1, but it might be like set when n is greater or larger than 5, and then it'll be 5. And I'll show that it is true for the lowest value, and then show that when you assume f of k is true, then f of k plus 1 is true when you use the f of k. So it means that for every f of k plus 1 is true. And you want to, if you are able to show this, you are able to make a conclusion that since it's true for lowest value and for every value, then the value above it is true. That means that for every value that it claims to hold true, it will be true. So that's gonna be proof by induction for you. And I'm really sorry for you guys because I didn't do any of these examples, but if you're watching this video, you probably had all the classes already, and it should just be a unit review for you. And there's plenty of resources online and also on Cognitive that can help you guys like review something that you've maybe forgotten or having a bit of trouble on. So really sorry I don't have any examples for you guys to work with today. Um, and also that you might notice like at the start of this, oh my god, this is like such great notes that I've got for you guys, and it's slowly deteriorating because I've gotten out of time and I'm tired and lazy. But what can I do here? Binomial theorem and accounting principle. So this is my favorite. I think it's really fun. So the binomial theorem, you need to know 2 formulas. It's basically expanding like binomials. So binomials are like 2 terms added together. And how I would think about this is like for a plus b squared, we know this formula is going to be a squared plus 2ab plus b squared. But how does this work for even higher terms? So if you were looking for even higher terms, you're looking at this one. And n over 1 is like a Pascal's triangle. So it's a this is a combinatory, and combinatorials you can calculate them using this here. We're using factorials, which I hope you guys know what are. So factorials are like 5 factorial is 5 times 4 times 3 times 2 times 1. So anyways, these are everything about the binomial theorem you need to know. But what if like n, what if the power you're going at isn't a whole number? What if it isn't integer? What if it's a decimal or a negative? That's when you use that general binomial theorem, and it's really probably the most tedious one out of all of them, but it'll definitely come up. So some mutations that I've seen this question occur is it'll ask you for like which root, like what is the coefficient for this part of x, and in most situations it'll be an integer, and you can find them using this. You could try to directly find the term here by setting the term you want to find for as like r. So you can find the coefficient, and remember to use the coefficient. So Pascal's triangle comes into play here because when n is 1, Pascal's triangle, the coefficients will be here. This is for n equals 2, n equals 3, and it goes so on. But it's only applicable if it's like low numbers, which is what normally is. So it'll be nice to like know some of the Pascal triangle numbers in your heart. Permutation and combinations. And it's a bit more fun unit, but if you don't have the intuitive ideas, then it's gonna be really difficult. So what a permutation is how many possibilities of this, and it is regardless of order. So for example, how many ways can you choose to watch like three movies in order? That's a permutation. But if it's a combination, then you're only choosing like these things where the order does matter. Sorry. Well, order doesn't matter. So, like, out of 10 movies, how many combinations of three can you find? Out of 10 friends, how many combination of two people that you can find? And it doesn't matter if you chose the first person first or the second person second, because you're basically getting a two people out at the same time. So that's how you can differ between permutation and combinations. And these are respective formulas for permutations and combinations, and there's a notation for it. But how I would think about this is, so when two things need to occur at the same time. So when, for example, if there's a like 1 in 2 chance that I hit this ball and a 1 in 2 chance that Daniel hits the ball, then you want to times these two values together because they're independent of each other and they need to happen consecutively. But for permutations, sorry, but when it's like when it's like a or situation, so like you want to add the combinations or permutations. So like when you want to add like the chances that of something happening when a person sits here and the chance of something happening when a person sits, or chance of something happening, the same thing happening when somebody sits here, then you want to add these two values together because they aren't independent of each other and they don't happen at the same time. So that's basically what permutation and combination is about, and it's gonna be really fun and easy if you have enough intuition on it, and but you're gonna struggle with it if you don't have enough practice going in. So yeah, and I would really recommend knowing how to use permutation combination on your GDC, because a lot of times you don't want to do you don't want to do this math by hand. Yeah, because like factorials go really crazy when it becomes too big. All right, that's like guys, great job. It's been like 30 minutes of like despair and doom, right? 1.11 is partial fractions. I think it's a relatively chill unit for HO content. Oh, I didn't take guess what it was HO content, but or not, but it'll be nice to know all these things. It's like so fun to learn about partial fractions. Oh my god, it's not. But so basically, I guess I'll do this example with you guys. So you want to factor this root, so it's gonna be x plus one. My eraser is huge. So this is gonna be the bottoms are gonna be x plus 1 and x minus 2. And you set these two as a and b. And you want to say that for a times a minus 2 plus b of x minus 1 is going to be equal to 6x minus 6. And doing this, you'll be able to solve for a and b respectively. So basically, it's more like a plus b is equal to 6, and you know that negative 2a plus b is equal to negative 6. So if you minus these, then you would get 3a is equal to 6, so a is equal to 4. If a is equal to 4, then b equals to 2. So you gotta remember to solve it, okay? So you gotta write down at the end that this will be equal to 4 over x plus 1 and plus 2 over x minus 2. So that's how you reverse the partial fractions, how you reverse. So it's easy to like take two fractions and add them together, but it's a bit harder to reverse engineer the process. And a thing to watch out for is sometimes you can't find the roots, right? What if it's like cubic roots and it's not intuitive to find them? You gotta use the rational root theorem. I know, everybody hates it, but you gotta do what you gotta do. 6% left. Okay. Yeah, and also like when you're having these problems, what if there's more variables or more like things you need to do? It might not be always easy to solve it using system of equation, where we will get onto later, which is here. Um, But another really easy way to solve it is going to be setting like x to 0, setting like one of these terms to 0. So basically like set x to 2 here and calculate them for what happening here. And it's going to hold true so you can find b and come back to a. So setting a term to 0 can isolate the term very easily, and that's a method I would really recommend. So sometimes system equation is like the more gnarly way, and I don't recommend it to like try to use it all the time. But yeah, last part, system equation. Um, so solving systems of linear equations, there's a lot of ways to do it. For easier ones, eliminate, substitute. If you have decimals, then graph it to find a solution. But what if you have systems of like 3 solutions? Then you want to use a matrix. So what a matrix here is like a set here. And how to write a matrix? So for example, if you have 3 system equation where you have like variables x, y, and z, if you have like x plus y plus z is equal to like 2, then you'll write like in a matrix, you'll write like 1, 1, 1, and then 2 here. And what you want to do with matrix is you want to make them look like a row echelon form to be able to solve for every variable. And the rule of how to solve with matrices is basically you can times the entire row by any number, and you can plus or minus any row between them. And you want to eventually use that to get to the row echelon form. And you know that these are the coefficients for x, y, and z. So, well, that's not the best coefficients to use, huh? For a, b, and c. So that's going to be how you're going to be able to solve these type of questions. All right, we're done with everything. That was more than 30 minutes of doom and despair. Yeah, but I hope you guys have a great test tomorrow. Wishing everybody getting a 7. This is Pascal, and he's gonna be manifesting like the test is gonna be easy, and then we all guess the right questions and stuff. So yeah, subscribe, drop a like, comment on what you want to see next. I really do think I'll be remaking this video again because like there's too much content to cover in such short time, and I'm not really well prepared in my content for this. So um really sorry there's no examples and stuff. I think it'll like be a really better video if I was able to like list out examples and show you guys what I'm thinking, because I like talk really fast a lot of time, and my mic is not good and the audio is like bad. Yeah, so make sure you subscribe and really enjoy making today's video. I hope you guys had learned something from it. You know, like you saw me doing it, you're like, oh, I should go learn this right now, and then you like save 3 points on the test. Yeah, so I'll see you guys in the next one. Bye bye.